Now that we've introduced confidence intervals in general, let's move on to talking about a specific kind of confidence interval called a bootstrap confidence interval. The previous kind of confidence interval that we constructed was known as a parametric confidence interval, where we assumed a specific distribution for our errors. In this case, we assumed that the errors had a normal distribution, in addition to having mean zero and being uncorrelated and identically distributed. So as we saw with permutation tests, those assumptions are not necessarily valid. And so the question is, can we still construct confidence intervals when we can't make the assumption that the errors follow a normal distribution? So to motivate the bootstrap confidence interval, let's talk about how we would approximate a confidence interval if we didn't have all the statistical theory that we know, if we couldn't just construct them using a t distribution or an f distribution. So in order to do that, we would have to approximate the sampling distribution of our statistic of interest. And so if we knew the distribution of our data, what we would do is we would sample from our known distribution. We would compute the relevant statistic for the sample data. We would then repeat steps 1 and 2 a large number of times so that we could get a sampling distribution for our statistic. And then we would estimate the sampling distribution of our statistic by that empirical distribution of these statistics from the simulated data sets. So what we're doing right here is we're just trying to estimate or approximate the sampling distribution of our statistic, just like we did with hypothesis testing. So how do we do this in the context of regression? Well, in regression, the random variable really comes from, or the randomness of our data comes from epsilon, the error. So we would generate epsilon from a known distribution. In our case, this is generally normal. We would form our data, y equals x beta plus epsilon, assuming that we knew x and we knew beta, which of course we don't know beta, but we'll do that for the sake of the thought exercise here. Once we generate our data, we would compute beta hat, the estimated regression coefficients, and then we would repeat steps 1 through 3 many times. And then once we had repeated steps 1 through 3 many times, we could estimate the sampling distribution of our estimated coefficients by simply looking at our empirical distribution of the estimated coefficients from the simulated data sets. So basically, we're just going to take the estimated beta hats and we would plot the distribution of them across all the different samples. So that's what we would do if we actually knew the distribution the data came from. Of course, we don't know that. So what does the Bootstrap method do so that we can approximate the sampling distribution? So instead of assuming the data comes from a known distribution, the Bootstrap method uses the observed data, the data we actually observed, to approximate the shape, spread, and bias of the sampling distribution of our statistic. And the Bootstrap distribution is always going to be centered at the mean of the observed sample. So it's not going to necessarily be in the exact same location as the true sampling distribution, but it should approximate the shape, spread, and bias. So what the Bootstrap procedure does instead of simulating new data is that it samples from the observed data. And surprisingly, this technique is actually really, really effective. And so instead of having to do a lot of theoretical calculations that are difficult or impossible, we instead substitute that by sampling from our observed data and calculating the statistic of interest. So in these graphics right here, which the code to produce these graphics is in the notes or in the R code for this chapter, what we have done is we generated some data, and for each data set, we took the sample mean and we looked at the empirical distribution. And then this solid line right here is the true sampling distribution of the statistic. Well, if we didn't make the assumption that we knew the distribution of the errors, we might use the Bootstrap method instead. And so what we did is we took our observed data, we randomly sampled with replacement in observations from the observed data set. We computed our statistic of interest. We did that a number of times. And then we plotted the empirical distribution, which is shown by this histogram here. And then the true distribution of the data, the same line that we have up here, is shown by this solid line. And you can see that though the empirical distribution that's in this top part of the slide looks a little better, a little closer to the true sampling distribution than the Bootstrap distribution, the Bootstrap distribution actually looks pretty good. But we didn't have to make any assumption about the distribution from which this sample came. whereas we did when we produced this sampling distribution up here. So how can we implement a bootstrap procedure in a regression context? Well, essentially what we need to do is we need to figure out a way to approximate the distribution of the errors. And the way that we'll do that is after we fit our linear model, we sample with replacement from our vector of residuals to get epsilon star, which is this sampled set of residuals. Once we have epsilon star, we sort of create a synthetic data set, y star, by taking x beta hat, so the fitted values, plus the sampled errors from our residuals. And then once we create this new data set, we're going to compute beta star hat, which is the estimated set of regression coefficients for the data x and y star. So basically what we're doing is we're using y star in place of our original data, and we're estimating the regression coefficients from the simulated data set. We repeat steps 1 through 3 a number of times, and then we look at the distribution of beta star hat. And that's going to be the bootstrap distribution of our estimated coefficients. And to obtain our bootstrap confidence interval, it's actually quite simple. Once we have our bootstrap distribution, we just take the appropriate quantiles from the bootstrap distribution. So if we wanted to construct a 95% confidence interval for a parameter of interest from a bootstrap distribution, we would just take the 2.5 and 97.5th percentiles of the bootstrap distribution. So in our context here, we're going to sample our residuals using the sample function, though it's very important that we use the replace equals true argument. We'll then use the residuals and fitted functions to create these synthetic data sets, and then we'll refit linear models using the update function. And the update function is just a way of taking an existing linear model and updating it with new data. And the reason you use the update function is that it's actually faster. Basically, the x part of the computation in the QRD composition does not need to be repeated, and so the update function is quite a bit faster. So let's actually look at the R code, even though it's in the notes, so you can get a better idea of what we're doing. So I'm going to set the seed here, 1, 2, 3, so that you guys can get the same results as me. NB is the number of bootstrap samples that we want to take. Let's set that at 4,000. And then for each one of my bootstrap samples, I'm going to need to store the estimated regression coefficients. So for each one of these data sets, I'm going to estimate the regression coefficients and store them in this matrix right here. My residuals, my epsilon hats, I'm going to obtain using the residuals function on my linear model. Preds is the fitted values. Okay, so these are the y hats. And what I'm going to do here is I'm going to generate a synthetic data set 4,000 times. So what I'm going to do is I'm going to take the fitted values, then I'm going to generate epsilon star. The way I generate epsilon star is by sampling my residuals with replacement. And so instead of simply permuting the residuals, it's actually going to randomly select a residual. And then after it selects one residual, it puts it back and then does the same thing n times. And so we're going to sample n residuals with replacement to create a new data set, which we call boot y, not booty. It's boot y, the bootstrap of the y vector. And then once I have my new data, I'm going to update my existing linear model, and I'm going to replace the original response with boot y, and I'm going to regress it on dot, and dot means all of the original variables in the model. And what this is going to do is it's going to fit a new linear model using the boot y response in place of the original response. But this is going to be faster than if we refit the linear model every single time. And once I fit my bootstrap model, I'm going to extract the coefficients from bmod and store them for later use. So let's do this. So I'm going to do this 4,000 times, and it should be relatively quick. Okay, we're done now. And once I have coefficient mat or coef mat. Oops, actually I need to name it. So what I'm going to do is I'm going to name the columns of coef mat using the column names of my Gala data frame. And now if I look at the names of coef mats, okay, that's still not going to work. So I'm going to convert coef_mat from a matrix into a data frame. Okay, you can see that I now have the names of my coefficient matrix. I can actually look at my coefficient matrix. Okay, so you can see the first 6 rows of that data frame, and what each column represents here is what each row represents is a set of estimated coefficients for the ith bootstrap sample. So for each bootstrap sample, we have a new data set. We estimate the regression coefficient for the new data set, and then we store it for later use, and then we repeat that, in our case, 4,000 times. So I have these, each column represents the set of estimated coefficients from the bootstrap samples. And once I have those, in order to construct my confidence intervals, I just need to take the appropriate quantile from each column. So I'm going to use the apply function, which applies the same function to each row or column of a data frame. So I want to apply the same function to the coef_mat data frame. 2 means apply to each column, and then I'm going to what I'm going to do is I'm going to use the function. It takes a vector and it's going to return the 0.025 and 0.975 quantiles of that vector. And now I can look at my confidence intervals. And so what these values represent is the 2.5 percentile and 97.5th percentile of each column of coef_mat. Now, so these are the bootstrap confidence intervals for each regression coefficient. Let's focus on the column related to area. If you remember, previously my confidence interval, my 95% confidence interval for the area coefficient was about -0.07 to 0.02. So my bootstrap confidence interval is actually a little bit narrower, but that's okay. Overall, it's roughly the same size. You wouldn't make really any different conclusions using the bootstrap method in comparison with the parametric method. And if you want to have a better idea of the distribution, the bootstrap distribution, we can plot the density of the estimated coefficients from each bootstrap sample. So this is going to take the bootstrap coefficients for the area regressor. I'm going to construct the density function, and I'm going to plot the density. So this is really the bootstrap distribution for beta hat area, and then these vertical lines represent the bootstrap confidence interval. Can do the same thing for adjacent if I wanted to. Okay, so I'm just going to take the density of the adjacent estimates, and then I should actually, there's a typo here, so this is doesn't correspond to the right numbers. So we should use negative 0.104 to negative 0.041. And where I'm getting this is from my bootstrap confidence intervals. So I want to plot using vertical lines to plot the bootstrap confidence intervals for adjacent. And I see those run from -0.1 to -0.04. And so I put the correct values here in my R code. Okay, so here's the bootstrap distribution for beta hat adjacent. And these quantiles represent the 95% confidence interval for beta adjacent. And so now we have constructed our bootstrap confidence intervals. We should interpret them. So let's interpret the confidence interval, the bootstrap confidence interval for elevation. So take a few seconds, pause this, and then see if you can't write the interpretation of the confidence interval for elevation. Okay, well, let's look at how we would interpret the bootstrap confidence interval for elevation. So we would actually interpret it very similarly to how we would for the for a typical confidence interval. So in this case, we are 95% confident that the coefficient for the adjacent predictor, this is not adjacent, it's elevation. We're 95% confident that the coefficient for the elevation predictor is between So 0.22 and 0.43. Okay. So that's pretty straightforward, pretty much identical interpretation to what we would do for our typical regression coefficients. So you may be wondering if you can use bootstrap methods for hypothesis testing, and the answer is yes, you can, though typically permutation-based methods are preferred. They're usually easier to interpret. And I should point out that there are alternative resampling methods for the bootstrap. So instead of sampling the residuals and using those to create our synthetic data sets, we could have instead sampled XY pairs rather than residuals, in which case we would actually be resampling the observed data rather than the residuals. However, if you're doing a designed experiment, then this is not very attractive, because oftentimes when you design an experiment, you set up your X matrix so that the columns are orthogonal. So that we would only use this if we were constructing bootstrap confidence intervals for observational data. And there's more complex ways of constructing bootstrap confidence intervals. There's a book by Davison from 1997 that has more details about that and many other aspects of the bootstrap distribution.